Okay, so we're looking at the idea of an average rate of change, and we're going to compare it with an instantaneous rate of change. So what we're doing is we're measuring how the graph is changing between points. Okay, so the average rate is between given points. So this is one value, this is another value. So we're going to measure how the function changes. So the rate of change is actually just measuring the gradient between the 2 points. Okay, it doesn't say how what else might happen between the 2 points, but it's just averaging what's happening. Okay, copy and come across. Okay, so let's have a look at an average rate of change between values for just this one function. Okay, so what we do is, for the first one, when x equals 3, when x equals 5, okay, so when we put 3 in, we got 3 squared minus 4 equals 5, 5 squared minus 4 equals 21. So the gradient, which is the rate of change, will be the rise. So the difference between those numbers is 16, divided by the difference between those two numbers is 2. So the average rate of change is 8. So it's increasing at an average of 8. But for b, let's have a look at what happens with b. When x equals minus 2 and x equals 2, we've got minus 2 squared minus 4, and that equals 0. And then we've got 2 squared minus 4 equals 0. So the gradient is going to be the change, which is 0, over the change, which is 4. So it looks like there's been no change, but in actual fact, it's averaged out things. So this is a parabola, and it's a symmetrical parabola with minus 2 and 2. In the first one, when we had 3 and 5, okay, there's a change in the graph that we can see. But what's happening with the second one is the graph is changing a lot, but on average it's changing nothing. So the average rate of change loses a lot of information, but it's still a measure. Okay, so copy that and come across when you're ready. Okay, so now we're going to look at an instantaneous rate of change, and what we're doing is we're measuring the gradient at a single point. Okay, so this gradient is actually just the tangent at that point. So the instantaneous rate of change is, rather than having an average, it's at a single point. And the problem is, how do you find a gradient? How do you find a rise and a run at a point? That's the question. Come across when you're ready. Okay, so to find the gradient at a point, we still need to find the rise and the run. But what we need to do is we have to make the run as small as we can, so that the gradients, so is right, like here's the point we're looking at. What we're trying to do is make this run as small as possible. So copy and come across. So what we're going to do is, the key point is we're going to have a look at what happens at 3, and we're going to look at what happens, okay, so the gradient is at 3. So we're going to measure what happens from in front, but we're also going to measure what happens from behind. Okay, and we'll see if these values approach the same thing. So we're still going to have this point. This is the key point, but we're going to make the gradient, the triangle, come from the right, and we're going to also look from the triangle from the left and see what happens. Okay, so I've still got the same function, x squared minus 4. And we're just going to use our calculator. And so when we have 3 squared, 9 minus 4 is 5. So the first value is 5, and I'm just going to use my calculator. So 3.5 squared minus 4 is 8.25. And I'm just using my calculator while you're sitting there. 5.61, 3.01 squared minus 4, 5.0601, 3.001 squared minus 4. Okay, getting smaller, but still got 5.00601. And now I'm going to go from behind, make it still going towards 3, getting closer to 3, but from behind 3. So 2.9 squared minus 4 equals 4.41, and 2.99 squared minus 4 equals 4.9401. So in each of these cases, we're going to find the change in y divided by the change in x. Okay, so we're still going to find the rise over the run for each of these. So the first one is going to be 3.25 divided by 0.5, and then the calculator that equals 6.5. The next one will be, I'm just looking at the values, so I'm looking at the next two values and we'll keep it going from that way. So I've got 0.61 divided by 0.1, so that's 6.1. Next one is 0.0601 divided by 0.01, so I've got 6.01, so we've still got the 6, and then the final one 0.006001 divided by 001, so now I've got 6.001. So you can see that it started at 6.5 and it's getting closer to a value. So let's see what happens from underneath. So gradient 5, so I'm going to subtract those numbers. So 5 minus 4.41 equals, okay, 0.59, and then 3 minus 2.9 so I've got 5.9. So I don't have a 6, but I'm not that far away from 6. And the next one, 5 minus 4.9401, okay, equals 0.0599 divided by 0.01. So if you have a look, jumping up too hard. Okay, from above, what value is approaching, and then from below, what value is approaching. Okay, it's approaching 6, it's approaching 6. So it doesn't matter which side we approach it from, we're still going to get this same value of 6. Okay? If the value was different, if the value that, if we're approaching it from the left and we're approaching it from the right and the value was different, then we can't find an instantaneous. And you can get those, but not in normal functions. Instantaneous rate of change. So it's important to know that the value has to be the same from above and below. If it wasn't, then we can't find a rate of change. Okay, copy and come across. Okay, so to practice average rate of change, there's an exercise 18C on Essential Mathematics. Thanks for that. See ya.